Remember to do that. Okay. And we're going to be using some of my slides again this evening for much the same reason, but in this case, it's maybe not quite as clear cut. We might also go to the Networking Academy slides as well, because in this particular instance with OSPF, they're pretty good. So first of all, is everybody comfortable with IP addressing to the extent of understanding what an IP address is and what the mask is, and how the two relate to each other to define the network and host bits? Is everybody comfortable with that so far?
Yeah.
Okay.
Yeah.
Okay. So we're going to continue on, keeping it simple with masks, network masks that are only 255, 255, 255, or some multiple of 255. We're not going to do any subnetting yet that will require us to use a different mask other than something that's a multiple, either 255 or some multiple of that 255. Okay. And does everybody understand the concept of a static route? Any question on static routes? We actually created static routes last week in class. You did possibly that lab afterwards. And no questions about that. Okay.
No.
Okay. What would be let's see. Well, what's one advantage? Let's just say, what is one advantage of a static route? Actually, it might be a little premature to ask that, because in a little bit we're going to be going into OSPF, but does anybody happen to know what an advantage would be of a static route offhand?
Maybe connecting to like in the same network.
Okay. So you could define a route within the same network if you like, and you don't have to rely on any routing protocol. You can specify a route that you might prefer packets take, though a routing protocol might come up with a different path for a different reason. So that would allow you to have, so it allows you to have, in some ways, more granular control, fairly easily, more granular control over which route a packet would take, okay? Now, what we're going to see when we get into dynamic routing, of which OSPF is one of the dynamic routing protocols, is that these routing protocols have update traffic. And we'll look at OSPF as not having a lot of update traffic, but it has some. And that update traffic can impact the bandwidth that's available across a link, whereas a static route has no update traffic. Once you define it, it sits in the router and it does its thing as long as the either the exit interface or next hop is available. And actually it would be the exit interface. If the next hop became unavailable, it wouldn't necessarily know that. It would depend upon what the link was. But it's important to understand static routes. They were widely used, even though every major environment will also rely much more heavily on dynamic routing. So I'm going to go ahead and pull up, I'm going to do a share of the slides. These are my slides for OSPF, okay? So first of all, I just want to refer to why are we talking about this? And we saw that we can create a static route to have packets go to a particular destination. We can also create a default.
Does everybody see the screen black or is just me?
I'm
Yes.
sharing the OSPF screen. Is it? Oh, my screen sharing is paused. There we go. Resume share. Let me try it again. Okay, let me, it said it was paused for some reason. Maybe I clicked on something.
Yeah, now we see it.
Okay,
And I rewatched the last video from Thursday, and you know what happened on your board, on your whiteboard? It doesn't record what you type, only few of the things that you type. It doesn't record the whole thing. If you watch, you'll see what happened.
wow, well, that's not too good. Okay, well, thank you for letting me know about that. That's not good. I'll have to explore that and see. I find the whiteboard cumbersome to use, so I'm going to tend to stick with slides, but that's good to know. Thank you for letting me know.
Is there any way you could use like the annotate feature on Zoom? And then
The
like
on Zoom?
the annotate feature where you just like write with your mouse or
The annotate, you mean? Yes,
yeah, and then
I
like
could
just
I
do it
could
on like
try
a
that. Well,
white
let me just try that right here. Because I see it there. Okay. We can do that. You can see that, right?
yeah. And then
Okay, well, I
you
was
could
gonna
just do
write.
like a blank space or something.
Right, right. Now that I don't think is gonna, that's not actually going onto the slide, but okay. So possibly I could do that. I've never tried the annotate. Yeah, do it on a blank slide and we'd be be able to have that
Yeah,
work for you folks.
just kind of hard with the mouse, but I
Yeah.
think that'd be better over the
Yeah,
other thing.
yeah, I actually have that one of those tablet with a the pen tablet that you can plug into your computer,
Hmm.
but and it comes a mouse as well. I found that to be a little awkward to use, but I'll see if I can just do this when we come up with some issues for this. Come up for a use for it. So, okay. All right. So, well, there we go. Nothing important on that as far as the message there, obviously. But thank you. I'll keep that in mind. So let's let me look at dynamic versus static routing. So static routing, you manually implement it. If something changes in the network, you have to change the static routes. One of the biggest drawbacks to static routing is scalability, meaning expandability of your network. As your network gets more complex, the ability for you to support it with static routes can become overwhelming to a point where it's no longer even workable. And of course, if something changes when you're not there to manually make a fix, the network can go down. So dynamic routing protocols basically can be used to keep your network connectivity active even when there are changes to the environment. If there are never any changes, of course, well, you wouldn't really have to worry about dynamic routes. But dynamic routing allows for the network to adjust to changes. So that's why it's referred to as a dynamic routing protocol. What happens with dynamic routing protocols, and there are a few different categories, but basically the routers are going to talk to each other and exchange information about the routes of which they are aware. And they exchange that information and then are able to calculate their new routing table if necessary. And then their new routing table allows them to maintain connectivity in the network as things change. So a router is always going to forward packets based upon its routing table, but its routing table can be populated by either static routes or dynamic routes. A default route is a type of route. It is not a way of putting a route into your environment. You can learn a default route through a static configuration. Your router can be configured with a static route that's also a default route. We did that last week. Or your router can learn about a default route dynamically from another router. Either of those are possible. And we'll see actually how we can do that in OSPF. So we have a dynamic routing protocol. And in the world of dynamic routing protocols, there are two types. There's something called distance vector, and there's another type called link state. There's actually a few more beyond that, but for our purposes at this level, we only have to be aware of two types, distance vector and link state. Now, a distance vector routing protocol is a routing protocol that sends its routing table to its neighbors. That's simply what it does, and it sends it usually periodically. So what would happen is every update period, a router would take its routing table and send it to its directly connected neighbors. The neighbors would look at the incoming routes from the neighbor router, compare those to what they had in their routing table, and if all of the routes that were coming in were already in the routing table, it would simply reset the update timer on those routes. So as a route is sitting in the routing table, it can time out if you don't get an update that confirms it's still there. And that's what a router would do. If it doesn't get an update from a neighbor that confirms that a route through that neighbor is still there, then it will time that route out and remove it from the routing table. So that's basically how a distance vector routing protocol works. Let's say you're sitting in a classroom, it would have like the three of us here. Let's say the three of us were here and we were in a row, and Georgiana was in the middle, Armando's on one side, Roger's on the other side, and no one could see each other. Well, if we wanted to know if everybody was there, or let's say Armando wanted to know if Roger was still there, he would wait for Georgiana to tell him about every 30 seconds, let's say, yep, Roger is still here. And then he would reset his timer and he would say, okay, for the next 30 seconds, I'm going to assume that Roger is there. If I don't hear from Georgiana, then I'll start to wonder whether Roger's there. And eventually I'll say, oh, I haven't heard from Georgiana about Roger. I'll bet he's gone. And that's basically how a distance vector routing protocol works. Okay. Something that is integral to the understanding of all routing protocols is that of a metric, or how far away something is. And there are different ways of measuring how far away something is. For example, how far away is a network? One way of measuring how far something is through hops. And we consider that if you have to go over one router to get to the network, that would be one hop. Okay, so actually I could just let's just see if we can do this right up here. Draw this. Boom, boom, this. Boom, boom. And let's say I have a router here. Oh, that's a great router. And I have a router here. It's a little faster than having to draw the circles, but the circles aren't quite as pretty. So let's say this is router. Let's say this is router. Let me just go over that. This is router 1, and this is router 2 right here. And this is network X. Okay. So router 2 is going to tell router 1, I know how to get to network X, and it's 0 hops. In other words, I can get to it directly. When router 1 gets that information here, it's going to put network X in its routing table, and it's going to add 1 hop. So network X to router 1 is 1 hop away, or I have to cross 1 router. Let's say we had another over here. Is this working, by the way, for you guys? I mean,
Yeah.
okay. So router 3 here tells router 2, I can get to network Y, and it's directly connected to me. Router 2 says, I can get to network Y going out that direction, and it's one hop, I have to cross one router. It passes that information over here, and it says, I can get to network Y, and it's one hop from me. Then router 1 is going to put that into its routing table and add one hop. And so Y can be reached out that direction, and it's 2 hops from router 1, 1 hop from router 2, and 0 hops from router 3. That's distance vector routing. I'm just going to go DV for short. Distance vector routing. Okay? It's fairly easy to configure. Its operation is fairly straightforward. The problem is it's a little slow, okay? It also tends to use up bandwidth more because let's say that this is happening every 30 seconds, which one of the routing protocols would do. Every 30 seconds, it sends the information over, and it sends its entire routing table. Well, if there's a lot of networks out here, then every 30 seconds, router 2 is sending to router 1 all this information, none of which has changed. It just keeps sending it. And router 1 looks at it, oh, okay, nothing's changed. Sends it again, oh, nothing's changed. So that consumes bandwidth here. But when something does change, so let's say that this route over here drops out, no longer available. Well, unless router 3 were to send information saying, oh, it's no longer available right away, router 2 has to wait for the information to time out in its routing table. Router 1 has to wait for the information to time out in its routing table. So that would be fairly slow. And the process of all the routers to agree again on how the network looks is called convergence. So that's an important term in the world of networking. Convergence is all of the routers agreeing as to what networks are available and how to get there. Okay? Convergence. Now, that annotated that slide. Now I'm really curious. Let me just see if I can. Okay, what's going to happen here? Okay. All right. So now we're going to go on to OSPF. Uh-oh. How do I get all the annotation off?
I think there's an option to delete it, but
I don't know. Let's see
I don't
here.
know what the command is
Okay,
for Zoom.
annotate. Oh, here we go. There's an eraser right there. There we go.
But I think there's an option where it erases everything.
Oh, okay.
I don't know what it is.
Okay. Well, there we go. That worked. Okay. I'll take a look over here. Color, undo, clear. Yeah, there's a clear. Yeah, over there. So I got a toolbar over here that's giving me options. Okay. So I will go back to my mouse pointer. Here we go. All right. So we're going to talk about OSPF. First of all, let's talk about O and the SPF, because the O stands for one thing and the SPF stands for something else. O stands for openly published. That simply means that it is not a private standard, but it is published out there on the internet. Anybody is allowed to use OSPF. You do not have to have a license to use OSPF. That's not true of all routing protocols. Cisco has some proprietary routing protocols that you cannot use in your network, even if your router would run them. That would be the first thing. Your router wouldn't run them. But routers are not allowed to run them without a license. So what you would have to, a company would have to do, and this has been done to a little bit, a small extent, but not much, is that let's say a company is going to put out a router that's going to compete with Cisco routers. They might go to Cisco and say, well, we want to run one of your proprietary routing protocols, and we'll pay a license fee, and then we can put that into our operating system, and then people can configure your routing protocol on our routers. That has happened to some limited degree, and it can happen. One of the reasons why OSPF is popular, one of the reasons, is because it's non-proprietary. No one has to go to Cisco and get a license. If they're running Cisco routers, they can run OSPF. If they're running non-Cisco routers, they can run OSPF, and the two can talk to each other. Let's say, and I've actually come across this, where a company says, well, we've got all these, we've got some routers, we want to buy some new routers, but we don't want to buy Cisco and then use their routing protocol, because then when we upgrade and we want to buy someone else's routers down the road, those other routers can't run that proprietary protocol. So that can be a reason not to buy Cisco or to stay away from the Cisco routing protocol. So if many companies that have Cisco routers that have a great proprietary protocol on them available for use still do not use that protocol because it ties them into Cisco for any upgrades and OS changes, things like that with other companies down the road, okay? So the O stands for openly published, available to everyone. The SPF stands for shortest path first, so these three go together, and that stands for the algorithm that is used. It's also sometimes called the Dijkstra algorithm. So the shortest path first algorithm and the Dijkstra algorithm are the same thing. It's an algorithm that OSPF uses to calculate the routing inside of its environment there. So it's an involved algorithm in the sense of that obviously it takes some computational power to do that. But we're going to learn basically how it works. Okay. So that's the OSPF name right there. Openly published, shortest path first algorithm. We're going to be looking at features, how it uses areas, how it operates generally, how it operates on multi-access broadcast networks. This will be Ethernet, so it's a long-winded way right now of saying Ethernet. Eventually, we'll understand some of the nuances with that, but right now, we're just basically looking at Ethernet. OSPF link state advertisements. So that's what LSA stands for, link state advertisements. We'll understand what those are. The metric, how it computes the metric or how measure to other networks. OSPF load balancing capability, basic configuration, and authentication. Okay. So, and to get a sense of what OSPF is as a routing protocol, it's probably one of the most widely used routing protocols in the world because of two things. One, because it's openly published and so available to everybody. And also it's what's called an internal routing protocol, meaning that it's used inside of an organization. It's not used to communicate from one organization to another. And so just about every organization with any type of sizable network would use OSPF. And because of its wide use, and it has some substantial nuances to it, you actually could possibly make a career if you were an OSPF expert, okay? If you were a specialist, a very, very, very good person in understanding OSPF, you could possibly make a career. Now, you obviously have to understand networking in general. You would have to have a broader knowledge than that, just because of that in which OSPF operates. It operates within a network, within security measures, et cetera, et cetera. But having expertise in that could be very valuable for many companies. Okay, so first we're going to look at OSPF features. I mentioned convergence. That is all of the routers in your network understanding how the network looks and agreeing on which networks are where and which ones are reachable and so forth. OSPF can come to that agreement very quickly. So that's called fast convergence. When I described distance vector routing, what we saw was it could be sort of a slow process as routes timed out and routers had to wait a while to update their routing tables. OSPF allows for very fast convergence. Now, fast is a relative term, and there are situations where the timers used by OSPF are considered today to be way too slow. And there are ways that you can make OSPF work faster. There's other protocols that can be run in conjunction with OSPF to make it work faster. But when it was originally designed, it was designed to be a substantial improvement on distance vector routing protocols. And in fact, it was. So it's considered to have fast convergence. It has a granular metric. So what does that mean? Well, let's say if you're measuring how far away something is, let's say you're at the campus in Cabrillo, and you want to measure how far away is downtown Santa Cruz and how far away is Watsonville. Okay, so you've got those two places. And you'd probably use miles, correct? And so you'd say Santa Cruz is, probably about 5 miles away. Watsonville, I think, is about 11 to 12 miles away, 13 maybe, so around that. So you'd say that is your measurement would be miles. Your metric would be miles. But let's say you wanted to be much more precise. Well, I just sort of rounded up there. It's 5 miles. But what if you wanted to know how far it was to, let's say, Front Street versus Pacific Avenue? Well, they're both about 5 miles away, right? But one is, about maybe 100 yards or 50 yards closer than the other. If you're using miles, you can't make a distinction between those two distances. But if you were using feet, you could. Or if you're even using yards, you could then say, to get to Front Street is this many thousands of yards. To get to Pacific Avenue is this many thousands of yards. And you'd say, okay, Pacific Avenue is 50 yards further than Front Street from Cabrillo, because you are using a more granular metric. In other words, something that allows you tighter measurements. OSPF does that, and we'll see how that metric is calculated. Now, OSPF supports variable length subnet masking. That's what VLSM means. We haven't looked at how VLSM would work. First of all, we haven't looked at subnetting in great detail, but when you subnet, you don't always end up with the same length mask for every single network. So if I have subnetted some networks down to one length and other networks down to a different length, with OSPF, I can provide information to the routers that will let them distinguish from one subnet to another. And that's called variable length subnet masking. We'll see how that works, and it will make more sense when we get into variable length subnetting. Okay, so a hierarchical design, that's one thing. And that hierarchical design supports route summarization. And that is a benefit of the hierarchical design. And let me just describe generally what route summarization is. It's a wonderful thing. It's why the world works, you might say. Okay, so on your home router, your router has a default route. Well, a default route is actually the maximum summary route. That one route stands for all the other networks in the world. So when you send something to your router and the destination is not something inside your home, but outside your home to the internet, your router knows where to send it next because it uses that summary route, which is a default route in that case. So if your router had to have information about every single network that was out there on the internet, it would have to have a tremendous amount of memory, first of all, and it would have to have a lot of processing power to go through all of those routes to be able to figure out which one matched the destination you were trying to get to. So route summarization allows a router to hold what's called a summary route, and the default route is the ultimate summary route, but it's able to hold a summary route and then route packets without knowing about all of the routes that are part of that summary. And all that the router needs is that one of the summary networks that is being summarized, one of those networks is actually still available. As long as it is, then the summary route will be held in the routing table. Now, an OSPF router, when communicating with its fellow routers, its neighbors, it uses multicasts. And a multicast address is one that is less than a broadcast, but sort of like a broadcast. It's to a group. And what that does is that allows the other devices on the network that are not running OSPF to ignore the OSPF packets. They don't have to process them. So if, for example, I were to say I have a very important announcement for the men in this class, Georgiana could say, oh, I'm going to ignore that because it doesn't apply to me. She wouldn't have to then take all the notes down. It would save her a lot of time. Okay. Well, that's what a multicast address basically allows, is that one OSPF router wants to talk to another OSPF router, and it sends to a multicast address known to the OSPF routers and ignored by the non-OSPF routers. And that is a substantial advantage. And then its final feature that we're looking at here is authentication. And the reason we want to have authentication is it's very, very easy to add an OSPF router to your network, a rogue OSPF router. A laptop, for example, will run Windows Server. Windows Server supports OSPF. Therefore, I could bring my laptop into work, plug it into the outlet, the plug for my Ethernet connector. Now I'm on the network. I'm able to communicate on the network. I run Windows Server as an operating system. I configure OSPF. And now what I do is I misconfigure OSPF so that it causes problems in my network. Bingo, we don't want that to happen. So there are different methods that we can use to protect our network from rogue or unauthorized OSPF routers. One of those methods is authentication, and we'll see how that works. It's not really hard to set up, but it's a valuable asset, a valuable reason to use OSPF. Okay, so OSPF is a linked state routing protocol rather than a distance vector. So that's going to mean that instead of sending its routing table to its neighbors, it's going to advertise the state of its links, and its links is the connections, as you see here, connections to networks. So when we get into our scenario, and if you remember our scenario, of course, we have two routers, each has two networks attached to the routers. So the routers would simply exchange information about those directly connected networks. Okay. And what happens is those link state advertisements are put into a link state database, and then the advertisements themselves are passed on to other neighbor routers. And what you end up with when you're done is that all of the routers in your particular area have an identical link state database. In other words, they all have the same LSAs. And then they each calculate their view of the network from those LSAs. Now, before it can exchange these LSAs, it's going to form a neighbor relationship with directly connected neighbors. That neighbor relationship is called an adjacency. And it will maintain information about its neighbors in a separate table called a neighbor table. Okay, so we now know about two tables that LSA works with. Its neighbor table and its link state database or link state LSA table. Okay. When it sends out advertisements, as I said, they are moved on to other routers. So essentially an advertisement is flooded within an area. And this also lets you know something in regards to an advantage of having areas, because we can keep link state advertisements from being flooded into certain parts of our network by designating those parts of our network as a separate area. So that's what they're saying here, is areas restrict advertisements, so we don't have to have the entire environment learn about every single LSA. So let's say that you had a company that had offices in California, it had offices in Texas, had offices in Wisconsin, and had offices in Florida. Okay, just for example, if you divided your environment into areas, then you wouldn't have to have LSAs that are generated in California be sent all the way over to Florida. That would be an advantage, okay? When you build an autonomous system, and again, we haven't talked about an autonomous system, but when you're running OSPF in one or more areas, and those areas are talking to each other, we call that entire environment an autonomous system. And every autonomous system should have an area 0, which is also referred to as the backbone, and all other areas connect to the backbone. You don't generally connect a non-backbone area to another non-backbone area. What you do is you connect every area to the backbone. And then what you do is you can configure summarization at the area borders, again, to contain advertisements and to reduce the size of routing tables as well. That's not only reduces the advertisements, but it keeps the routing table size very manageable. And when you have a small routing table, then you're able to process the lookup of a packet much more quickly. When you have a router that has interfaces in 2 or more areas, that router is automatically an area border router. So you don't tell a router you're an area border router. What you do is you tell a router one interface is in this area, another interface is in a different area, and the router says, oh, then I am an area border router automatically. And it will behave accordingly. So what is the process that OSPF is going to go through? The first thing it does is it will form adjacencies. In other words, it will find its directly connected neighbors and go through the process of building a neighbor relationship, and it calls that an adjacency. But it will not do so unless certain criteria is met, and we will see some of the parameters of that, and that will often be a test question in the CCNA exam, is whether 2 different routers would form an adjacency given their configuration. Once you have this neighbor adjacency, it's going to flood out LSAs, and it's going to send those out to that multicast address. Multicast addresses start at 224.0.0.0. 224.0.0.5 is a multicast address specifically allocated to OSPF. So only OSPF uses 224.0.0.5. When the LSAs arrive, they're put into the LSA database. At that point, once it has its LSA database collected, it then is going to calculate the shortest routes to the various networks. That's the Dijkstra or SPF algorithm. And once it calculates those routes will go into the routing table unless there is some other issue that arises with competing routes from other routing protocols. So we can look at that. But for right now, this is what would normally happen, is that OSPF calculates routes and then puts those routes into the routing table. And that's the third table that OSPF deals with, is the routing table. So we have three tables that OSPF primarily deals with: the routing table, the neighbor table, and the LSA database. Now, how does it let its neighbors know that everything's still hunky-dory, where I'm still here? It sends hello packets, and a hello packet by default is sent every 10 seconds. Every 10 seconds, it sends out to its neighbors and says, I'm still here. And the neighbor then resets the timer for that neighbor and any LSAs associated with that neighbor. Okay. However, if there should be a change, for example, a route should go down or a new route should appear, then it will send an update at that point. Okay, so when we have a multi-access network, well, what would be a multi-access network? Well, Ethernet. You have Ethernet and you have multiple devices, multiple routers on the same network. What you want to do is not have all of the routers exchanging everything with each other. That traffic becomes a bit onerous. So what OSPF is designed to do is to elect a designated router. And that designated router will be the one that collects the LSAs. And then instead of sending, then it will send those out to all of its neighbors, the non-designated routers or backup designated router. But the other designated routers are not talking with each other and trying to exchange information. It's basically a hub and spoke exchange. So what happens is the first router that comes up automatically becomes the designated router. The second router that comes up becomes the backup designated router. And all others automatically become other designated routers. That will remain until something changes. If the designated router goes down, the BDR automatically becomes the DR, and a new BDR is then elected. And at that point, an election process is undertaken, and we look at the router with the highest interface priority on that network. And if they tie on that, and by default they would, the priority on a interface by default is 1. So by default, they would all tie. And then if they do, then we look at the OSPF router ID. And that can be a tricky thing to discern on a router because that is calculated in a certain way. We're going to look at that. So the priority is not for the OSPF router itself, but on each interface. So you might have router 1 on one network has a priority 1 on the interface on that network, but on another network, it has a different priority on the interface that faces that other network. So what happens then is that if you don't change the default, of course, it's going to be 1. If you want to set the priority as something other than 1, there is a command to do so. IP OSPF priority, and then the number. The reason that you would do so is that you might feel that due to your topology or router strength, you want certain routers to always be either the DR or the BDR. If you do set it to 0, it can't become a DR. So then how do we set the router ID? This is different than the priority. The router ID is a global thing. It applies to the router for a given autonomous system, okay? So you can run OSPF in a way, and this gets a little bit involved and might confuse you. For right now, we'll just say we're going to set the OSPF router ID for CCNA purposes will be for the entire router running OSPF. You can use the router ID command. If you do that, when the router comes up, it will use that ID that you set. If you haven't set it and you have a loopback address, it will then choose the highest loopback address. If you do not have a loopback address, then it looks at the highest active IP address on that router. So this is something you'll need to know for the exam. It's also something you'd want to know if you're out there configuring OSPF and you want to control the router ID. There are reasons to control the router ID. There are reasons to use loopback addresses, and those will become more apparent as you get more familiar with all of this. But for right now, just need to know that priority, you might say priority method there for setting the router ID. All right, a lot of stuff here. You're sort of like getting all this poured in at one time. Is a wow, one big, okay. Let's look only at this right now. Sent by every router, LSA type 1, and it advertises its own OSPF interfaces. I think what we want to do is flip over. I'd like to flip over to the scenario and talk about this, show you what this actually means, okay? So let's do that. I'm going to stop this share. I'm going to share my packet tracer environment. So I have two routers. Each router has two interfaces. If I configure both of these routers to be in the same area, then this router here is going to create one LSA that advertises that interface right there, and one LSA that advertises that interface right there. And after it forms a neighbor relationship with this other router, it will send those two LSAs over to this router, and this router will hold those two LSAs in its LSA database. This router will do the same thing, create an LSA for that interface, an LSA for that interface, and send it over here. So this router here will have those two in its database, as well as, of course, the two that's created. So when we're done, these two routers will each have 4 LSAs. They'll have one for this interface, one for that interface, one for the neighbor's interface there, and the neighbor's other interface there. They'll have identical LSA databases. Now, the information, the way that they process that, will end up with a little different result, because when this router here processes how to get to this network here, it's going to say, just go that way. But when this router processes how to get to this network here, it's going to say, you go out there next. But that's simply a matter of how the router would calculate its path to each network, okay? Any question on that? Okay. I'm going to go back to our slides and move on a little bit further. Okay. Let's not worry about LSA type 2 or 3 right now. We're getting this to be plenty involved as it is. So I'm going to skip down to the OSPF metric and hope that this thing doesn't start looping. Oh, good, it didn't. Okay. So the OSPF metric is referred to as the cost. Okay. The question is, how is the cost calculated? And that can be different on each operating system. In other words, Cisco might do it one way, Juniper might do it a different way. But well, the way that Cisco does it is they take 10 to the 8th, power of 10 to the 8th divided by the bandwidth of the interface. And that's how they come up with the cost associated with that interface. So what they're trying to show you here we are on this router, there's a destination out here. To get to this destination, we can go this way, going over 1, 2, 3 routers, or we can go that way, 1, 2, 3, 4 routers. Well, if we were using hops, in other words, we consider going over a router 1 hop, this would be fewer hops, but these are much slower links than these. When these routers advertise these links to this router here, and these routers advertise their links to this router will see that the cost or the metric to get to the destination is much lower going this way here. A lower cost or lower metric is better. Just like if you're going to go buy something in the store, a lower cost is better. So what would happen then is that OSPF running here would say, the fastest way to get to this network over here is to send packets out this path here. Obviously, if one of these links went down, OSPF could then use this path. But as long as these links are available and these links are available, OSPF will choose the lower path, even though you're crossing more routers. There's also something called load balancing, okay? So with load balancing, what we mean is we have a packet that arrives here, or packets, I should say, multiple packets that arrive here that are going to go over to this destination. We've learned that this destination can be reached this way or it can be reached that way. So we have 2 paths, but with OSPF, we only load balance over equal paths. And by default, up to 4 equal paths. By default, we can change that up to a maximum of 6. So let's say these 2 paths here were equal. We'll just say that whatever the metric is, it's the same going this way, and the same going that way. As packets come into this router going to this destination, packets will, some will go that way and some will go that way. We'll just basically alternate. Packet goes that, packet goes that way, packet goes that way, packet goes that way. That way, the advantage to our environment is this. Now, not all of the traffic is impacting one of the paths. We're sort of distributing the traffic over 2 separate paths, meaning that each of these paths is less impacted by the traffic. Okay, so load balancing is a good thing. OSPF only supports load balancing over equal paths, and by default, only 4 equal paths. Okay. To configure OSPF is fairly straightforward, but we've got a couple of nuances to add in here. We go into the global config mode and we go router OSPF, and then we add a process ID. And this is a number that we make up. We might have that dictated to us by the administrator so that there's consistency across our network. But the process ID in one router does not have to match the process ID in another router. In fact, the 2 routers will never know that one is using a process ID that is either the same or different than the other. The process ID is for internal purposes only. And the implication of that is that you can run the OSPF process more than once if you use a different process ID each time. And that is true. For our purposes, we only need to know that the process ID is something unique to the local router, not shared with other routers. We won't have to worry about running the OSPF process multiple times in a single router. That's potentially a little bit more advanced topic. Not tremendously so, but just know that's what it's for. It is not an autonomous system number. So it's not a number assigned to our group of routers that are working together to exchange routing information. Okay. So we go router OSPF process ID, we press enter. This puts us into the configuration mode for OSPF. We then have to tell OSPF which interfaces are you actually running under this process as OSPF, and of those interfaces, which one is in which area, okay? So the way we do that is with what's called a network statement. We start off with network, and then we put in a network number. We follow that with a wildcard mask, which is not a subnet mask. Often it is the inverse of a subnet mask, but you must understand it is not automatically the inverse of a subnet mask. Okay, we want to understand wildcard masks specifically. We'll use them later. They're used for many things in Cisco routers, but it is not a subnet mask. After we put the wildcard mask, then we tell the router what area this interface should be in. That would be done for that interface. Okay. So when you do a routing protocol, if we do a show IP protocols, we'll see that our routing protocol, OSPF 1, they've used 1 as the process ID, and it's routing for these networks here. Those are wildcard masks, and they're both in area 0. Okay. Now, what we need to understand is what is a wildcard mask and how does it work. So let's do this. Let me go. I'm going to stop this share. Actually, let's take a break because this has been a lot of stuff. Let's take a break. Let's come back at 7:20, be 19 minutes, come back. And at that point, we're going to flip over to, going to be on Packet Tracer. And at that point, I will configure OSPF on these 2 routers. We'll use various show commands and we'll make this work. So let's go ahead and this point, get this thing here. We're going to pause our recording. Yes, I didn't resume it.
Oh my goodness, I was counting on the fact that I'm going to review this to do it myself.
Okay.
Is it also on the Network Academy site? It is?
Yes, but
Okay, the same example?
And I sent out this scenario and I sent out a lab earlier, and those will guide you through this to a degree as well.
But like the commands are in the network on the Network Academy site?
Yes, they are in the Network Academy, but they're going to be not in the course that we've created, because I jumped to a different course because I wanted to have this follow with the static routing. So use the lab that I sent out if you can, and I'll send along the slides and send along those. I'm trying to think what else I can send. You know what I'll do is I can create those other, I'll create those other courses and put you guys in those other courses as well.
Is it okay? Is it hard to make a slide or 2 with the commands that you ran today?
No, and let me see here.
Really, I should have write them down, but I didn't. From now on, I will.
That's okay. Let me just for a second here. The commands are in this. Yes, the commands are in the slides that I'm going to send out. Okay.
Did you send a reading assignment out for this beforehand?
I did. I sent out a lab and a scenario
That was today. You sent it,
today, this afternoon, yes.
but you didn't send it. You didn't send out a reading assignment or anything. Did
No,
I?
not a reading assignment, but I sent out a lab. So what I'm gonna have to do is create the other class. And I didn't realize that this OSPF stuff was pushed so far back in the Network Academy. I wanted to have it flowed where we were talking about routers, routing, static routes, and dynamic routes in succession. And they've broken it up in the way that they present it in the academy. So I'll have to create 2 more classes for you folks. One for the SRWE and one for the last class, the 3rd semester. And then, okay.
I have this. I'm recording this right now, so
Right, you're recording it. Okay. Could you share you recorded everything that I talked about since the break?
Yes, but last week it didn't work. So
Okay.
So I won't know if it worked until after the class ends, but I can put it on YouTube with your permission, though.
Sure. Oh, yes. The other thing, what you can do is just send it to me and I can send it along to them.
Well, it's gonna be a gig, so it's too big.
Oh, I see.
Right.
Yeah, okay. I understand. Let me just go through some of the commands. Let's do first of all, from here, do a show IP route. That shows us our routing table. Show IP protocol shows us the routing protocol process that we're running. Okay. Show IP interfaces brief shows us the status of our interfaces. Show IP OSPF neighbors shows us the status of our neighbors, our neighbor table, and show IP OSPF database shows us our LSAs, okay? So there are the commands, but I can send them out in an email. And I believe, like I said, I was looking over there at the, when I looked at the slide presentation, all those commands are in the slide. Interfaces, neighbors, yeah, there's actually some other commands that are in there. Plus, if you look at the, let's see what, let me just do a real quick check on the, yeah, it shows how to create loopback interfaces. I think it does. I know we've got them in there. So to create an interface, it's just interface LO0. It's a loopback interface. And I'm not sure if I have the command, but okay, I've got show IP OSPF interface, already one, figure. Okay, so yeah, it does. There's a command, interface loopback 1 or interface loopback 2, if you want to call them 1 or 2. So you'll find in the lab there are commands for creating the loopback interfaces, and then you assign the IP address just like you would to any interface. So if you look through that lab, that should give you some practice. It actually tells you also how to configure authentication. Okay. And that will be something that you would want to know for the CCNA exam, as well as just general principles. So this is a lot to get in one night. Okay, it's a lot to get. Trust me. So we can go over this next Thursday. Happy to do that. We'll go over this and confirm all these commands, reconfigure how to establish this. And if you want to right now, if you want to try and just configure this scenario, don't necessarily go through the lab, just configure the scenario that I sent out with OSPF. And I'll just stay online here And you folks can do that. We can take like a 10-minute break and then at 8:15, start up and have you folks configure OSPF on the routers, and I'll stay here until you're done doing that. Would that help?
I'd have to review things.
Well, do you want me to walk through the whole process again?
Can you do it on Thursday so then we can maybe the only person just need to prepare it is Armando. I don't know about Georgiana.
Well, what I can do is just start this whole thing over. In other words, just start with the scenario, open it up, and show you the commands. Just go through them one more time. It's certainly not a bad idea to practice.
Yeah, that'd be great.
Okay, yeah, let's do that. So I'm going to stop this share.
Can I have ask a quick question on the packet tracer lab that you thing that you sent us?
Yes.
Why PC1 and PC2? I've been looking at with IP config. Why do they have the same IP address?
Oh, they do? Let me take a look at that. I'm going to stop this share. I'll take a look at that just a second.
172.116.1.10.
Okay, okay, so let's okay, that's not in there. Let me check. You know, they're not part of the lab, and I probably got that left over. So let's do this. I'm going to go to this scenario. I'm going to reload. Actually, I'm going to just reload each router. That's what I'm going to do. So router 1, I'm going to take you through the process of reloading this router. We'll do the share, and we'll look at that part too, okay?
Okay.
So we're going to start with router 1. Share that. Okay, so let's look at have I saved anything yet? Show start. I think I did save something at show start, did I? Oh, there is yes, I saved everything, so I wanted to do it. Let's see, race start. Okay, so I'm going to erase what's in NVRAM, confirm that. Then I'm going to do a reload. And do I want to save configuration modify? No, I don't want to save it. Reload. Okay, so now I'm reloading the router. I'm going to do that on the other one while that's reloading. EN. Escape. Yeah, that would be. Oh. Restart. Okay, reload. I'm reloading both routers and I erased everything. So that means we have no addressing anything. That'll be okay. So then we'll fix all that. So let's go back here to my share. Stop that share and then do a new share. Okay. Router 1. Okay, so no, we don't want to do anything with the initial configuration dialog. EN. Now what I need to do, first of all, is configure my interfaces so that they work. So this would be good review. Config T, interface FA0/0. Stop me if you want me to slow down on this. I'm just going to get this done. 172.16, 1.1. 255.255.255.0, and then no shut. Okay, then interface S1/0, I believe it is, IP address 192.168.1.1. Shut. Okay, and that should take, let's just do a write on that. Okay. Now I'm going to go to the other interface. Well, first of all, do a show IP route just to see that we won't have anything other than the one. Oh, they're both there. Okay, so Everything's up and up. That's sort of interesting. I'll have to take a look at what's going on the other router to see why that is. In other words, where is my router 2? Okay. Okay, so let's look on router 2. Show run. See what we've got going on in there. Interface. Well, I erased start. Reload. 1.1. I have OSPF, and it's got router OSPF running, so I'll have to take that out. Okay, config T. OSPF 25 or okay, so now we're good. All right, so we now have the routers just addressed but not configured. I'm going to now configure OSPF on router 2. Config T. And I'm going to give this router, give it a name. I've seen that I left that out. So host name router 2, just so we can see that when we're on the prompt. Router 2. Okay. So to configure router 2 with OSPF, it is router OSPF and then a process ID. Again, I'm using 25 just because I am. Okay. I'm going to issue now network statements. I start with the word network, and then I put in an IP address. I'm going to put in the IP address of the Ethernet 172.17.1.1 with a 0.0.0.0 mask, and that will go into area 0. That's a wildcard mask of 0.0.0.0. Enter. And then I'm going to use this method here to not have to type it all out. 168. Okay, so 192. Oh, that's right. It's a 1.2, not 1.1. There we go. And do I have an interface? Do I have an LO0? I think I do. But I'll configure that a little bit. Control Z. Show IP route. Okay, so I do have a loopback interface. It's already configured. I'll reconfigure that or put the commands in again, just so you have it. And so those are my 3 directly connected networks. Okay. Sort of a pain the way it's, okay. To configure a loopback interface, it is simply int LO and then the number. I'm using LO0. Whoop. That worked. LO, I guess it took int LO0. Yeah, there we go. Okay. IP address 11.1.1.1. And then I put in a mask of 255.255.255.0.
But isn't this already done? It's up there.
Yes, I'm putting in the command so you can see the commands.
Oh, sorry.
Yeah, no worries. There you go. So yes, it's already done. I just wanted you to see the command entered. Okay, there you go. So now this router is running OSPF. I do a show IP protocol. And you see I'm running OSPF under process ID 25. It's used the loopback interface for the router ID. And everything else is as we would expect it. Okay, so I'm now going to stop this share and share router 1. Router 1, show IP in brief. We've already configured that. That's why it's working. We do a show IP protocol, and I don't believe, nope, so it's not running. So now we're going to configure OSPF. Config T, router. OSPF 25. Now we have our network statements, network. 172.16, 1.1, 0.0.0.0, area 0, network 192.168.1.1, 0.0.0.0.0, area 0. I don't think I have I don't have a loopback interface configured on this. That's fine. It would just affect the router ID if we'd had one already. But we see that the other neighbor right there, the other neighbor, their ID is set to their loopback address. Okay. Control Z and do a show IP route. And here we see we're learning through OSPF how to get to their serial 0. Now, there's a good question. Why, and I'd have to go back, we have to look at why am I not knowing how to get to their network or their loopback interface? So there's something wrong with the configuration in router 2 that it's not properly advertising. It might be because of I entered it twice. I'll have to see. I'm going to go back to router 2. I'm going to try and troubleshoot this and see why router 2 is not advertising that network. So let's do a show run. I'm going to see what the configuration is. Okay. So there's 11.1.1.1. Okay. So the loopback interface is there. Show IP protocol. And we're only routing for these networks. So we're missing a network statement. Let's do a show run and see if I have that network statement in there, maybe misconfigured. No, I don't have the network statement in there. That's why. I thought I did. So I'm going to go config T, router, OSPF 25, and then network 11.1.1.1, 0.0.0.0, area 0. Bingo. And now I should have that. Still, it's in my routing table, of course, already, but I'll be learning that on the other router through OSPF. On this router, I'm learning about the 172.16 network. All right, I'm going to stop this share and I'm going to bring up PC out here, PC2. You said the PC2 was not properly addressed. Default gateway is right, interface FA0. Looks like it's addressed there correctly. So it's 172.17, 1.10. Okay. PC1.
So I have on PC1, the IP4 address is 172.16.110.
Correct.
And then on PC2, 17.
Yeah. So it's
1.10. Okay.
So it's okay.
Yeah.
Right. So I'm going to share this screen here. I'm going to be back on router 1. Okay. So our PCs are correctly. So now I'm on router 1. I do a show IP route. And now I can get to the loopback interface. So that shows you, hopefully demonstrates with my little omission there, that in order to advertise a network, you must have a network statement under the routing protocol. That's how you tell the protocol what networks to advertise that are directly connected. Okay, so now I should be able to ping 11.1.1.1, and I can. Let's see, I should be able to ping everything over there, 172.17.1.1. and then 117.1.10. And can we ping that? Yeah, that works too. So it looks like we have full connectivity in our environment right now. Okay. Any questions about the commands that I've entered? I know that they sort of go blasting through there when I'm doing this on the screen, but just wanted to check on that.
I don't have questions, but still I will have to do the same I did with the other lab.
Well, that's okay. You know, I've done this. Well, how many times have I done this? I don't know if I can, since 1998, about 25 years.
Yeah, so
so-
yeah, what works for me is to take some time and review the video and then write them down and
Yes,
yeah, do it that way.
exactly. It just takes practice. And in 25 years, you'll have it down. There'll be nothing to it.
In 35 years, I should be retired.
And that might be a little too late. Okay, well, hopefully it'll happen before then. It didn't take me 25 years, but when you've done it well, actually, you know, I teach this once a year, and so I get a little rusty in between classes. But having done it, you know, over the 25-year period, I mean, I was teaching Juniper for a number of years and other things. But when I first started teaching Cisco, I was just teaching Cisco like 2 or 3 weeks, 5-day classes, 2 or 3 weeks a month, you know, for, you know, month after month. And I'll tell you, you do learn it. It's, you know, there's nothing like repetition, and that's all you have to do is just repetition and look things up when you have questions. But the repetition, eventually it will come to you. And you never know all of it. That's all there is to it. There's just no way to know all of it. If you learn one part really well, there's some other part that you won't know quite as well. That's all there is to it. Okay. So hang in there.
So in your class, you switched from 14 back to 12, right? From module 14 last class to module.
No. So module 12 is the numbering that I use for my own modules.
Oh.
Okay, don't worry about that. That should go with I sent you a scenario and I sent you a lab. They're both number 12, but that's my own numbering for my own. Don't worry about the numbering on that.
Okay.
Okay, I'll have to create classes for you guys, the second and third classes, so that you folks can access all of the materials up through the third semester. But for right now, what I'm providing you was enough for you to learn basically OSPF. Now, what we're going to do after this is we're going to go back and we're going to get back to some of the more basic things like Telnet, configuring Telnet so that it works, and practicing with different nuances in Telnets and CDP. And then we're going to look at switching. We'll start to get on switching in detail. But I'm not really crazy about the way they teach the course. And it might just be because I'm used to a different way. But I like for someone to come in and learn basically routing. And once they learn routing, then you go back and you learn switching. And it's really, at that point, it's not that difficult. Switching then becomes just sort of an add-on. And but there's a lot of nuances to switching that, you know, you have to get comfortable with. But once we understand basically routing, which is connectivity in the network, then we understand how the network basically works. With switching, switches are plug and play. So if you never understood how a switch worked and you just plug things in, everything would work as far as the switch goes. For the most part, it would all work. So it's the routers that have to be configured in order for them to work. The switches, you configure them to optimize the way they work, but they are basically plug and play devices. So we can do all this. There's you know, switches on each of these networks as we see here, but we haven't configured them yet everything's working. So that sort of gives you an idea how much you have to configure a switch to make it work. Okay. All right. Yeah.
I interrupted Roger. Roger, you wanted to say something. Sorry.
Okay.
No, I'm okay. Do you still want me to post this to YouTube? What I have?
Can you post it privately so that only people with the link to it can open it?
Okay,
Yeah, do it that way. That'll be fine. And then you can email the link to me, or you have the addresses of other people. You can email the link to them directly.
okay. I won't know if everything recorded properly until after the class and
Right. But
whether you two will let me allow to upload something that
sure. Well, I've recorded most of this, so I'll post this recording later this evening as well.
Okay,
So we'll have both recordings available. I'm going to create the classes so you have access to the class materials. And of course, you can send me emails with questions. I've given you the lab. If you go through that lab, hopefully it'll make sense and you'll be able to make that work. Get some more practice with OSPF. But essentially right now, with the scenario, the very simple scenario that I provided, or you can just go back to the default scenario, the unconfigured scenario that I provided originally. You take that scenario and just build it. Just build the scenario, address it, then set up a static route for practice like you did last week, and then take that out and set up OSPF. And when you do this and you see how these things work, this is how you learn. You sort of experiment around with things and you find out, what things are still a little bit confusing. I remember when I first started teaching networking way back. This was more than 25 years ago. I started in teaching Novell networking back, well, I won't even say how long ago, but it was quite a long time ago. And my first class that I taught, I had created the class myself. And when I got to this one section of the class, I realized that I still had some questions on it because when I went to explain it, I didn't explain it really well. It's like, oh, okay, that pointed out to me what I didn't understand. And sometimes that's what you have to do. If you really want to understand this, try and explain it to somebody else. And when you can't explain it, then you know what you don't understand. So it's a good way to sort of uncover the areas of your learning that aren't solid. So, any other questions that you want to go over for this evening?
So the erase, we don't have to do that, right? That you did because you already created everything, and then you click erase to remove everything and do it again for us to have this video.
Yes, you don't have to do that. If you just take the scenario that I sent out, it doesn't have OSPF configured in it. It does have the IP addresses for the interfaces. That's if you take the scenario that I sent out tonight. If you take the original scenario, which also basically is the same thing, it just doesn't have the IP addresses on the interfaces, then you have to just start back a little bit further and configure the IP addresses and then configure OSPF. So you could work with either scenario and make it work.
Got it.
Okay. All right. Well, I will send this recording out when it is ready, which will probably be not too late this evening, probably be about 20 minutes before it's ready, has to be processed. And then I'll send out information about the other classes. Okay.
Okay.
All right. And I can start sending out some practice questions here before too long too, so you can sort of do some practice question exercises and see if things are gelling for you that way as well. Okay, you'll have fun with those.
Cool.
Okay. All right. Well, if there aren't any other questions, we'll go ahead and sign off for now, and I'll see you folks on Thursday.
okay.
Bye-bye.
Bye.
Bye-bye.